Hello everyone, I am Sunita from Engineering Physics 3rd year and today I will discuss about inductive transducer. Inductive transducer works on the principle of electromagnetic induction. Self-inductance or mutual inductance is varied to measure required physical quantities like force, pressure, velocity, etc. Inductive transducer is of two types, simple inductive type or mutual inductive type. Simple inductive type transducer is a single coil is used to measure the required parameter. The change in displacement changes the permeability of the flux produced in the circuit, resulting in a change in inductance of the coil and the output. The output can be calibrated in terms of the measurement which is to be measured, and this is the circuit for a simple inductive type. Now, simple inductance type is again divided into two types, single coil inductance type and hollow coil inductive type. In single coil inductive type, when the armature of the circuit is moved, the air gap between the magnetic material and the permeability of the flux produced in the circuit changes. This results in a change in inductance in the circuit. This type is used mainly in counting the number of objects. In hollow coil inductive type, the magnetic core can be moved inside the hollow material, which has a coil wound around the hollow magnetic material. The output is proportional to the input and can be calibrated in terms of measurement. The air gap decides the change in the coil's magnetic field and the flux link. And second is mutual inductance transducer. Here transducers work on the principle of changing mutual inductance. These coils include their self-inductance which are indicated by L1 and L2, and then mutual inductance can be calculated by root over L1 into L2. Here K is called coupling coefficient, mainly depends on direction and distance between the coils. The displacement can be measured by fixing one coil and make secondary coil movable. This coil can move by power source whose displacement will be calculated. The change in displacement coefficient coupling distance can cause a change in mutual inductance. This mutual inductance change is adjusted by measurement and displacement. In this type, two coils are used for mutual induction, one for generating excitation and another for output. The voltage difference between the two coils depend on the movement of the armature. When the armature position is changed by connecting to the movable mechanical element, then the inductance changes. The air gap between the armature and the magnetic material and also the voltage induced in the coil depends on change in armature position, and this is the circuit diagram for mutual inductance type transducers. Now, working principle for inductive transducers. Generally, inductive transducers work on the principle of changing one coil's self-inductance or changing two coils' mutual inductance and eddy current production. The voltage difference and change in inductance result from the change in flux in the coils, secondary or primary coils. Now, self-inductance can be calculated by L is equals to N square by R. L is self-inductance and N is number of turns in the coil, and R is the reluctance of the coil. Now, reluctance of the coil is calculated by L divided by mu A. L is length of the coil and mu is permeability of the coil and A is cross-section area of the coil. Now, from this equation and this equation, we can calculate self-inductance is equals to N square mu A divided by L. Now, this A by L can be denoted by G, which is a geometric factor. So overall self-inductance can be varied or changed by changing number of turns, geometric factor and permeability of the coil. Change in mutual inductance. We consider the two coils which have self-inductance L1 and L2. The mutual inductance can be calculated by K into root over L1 into L2. Here K is denoted by coefficient of coupling. The mutual inductance can be changed by varying the self-inductance of the individual coils or by changing the coefficient of coupling. The factor K depends on distance and orientation of the coils. So now LVDT, linear variable differential transformer, is an example of inductive transducer. LVDT is the most widely used inductive transducer which converts linear motion into electrical signals. LVDT is a passive inductive transducer that requires an external source of power to operate. It uses coils and an alternating magnetic field to produce an analog output voltage, making it a variable inductive transducer. Thus, the linear variable differential transformer measures distance along linear axis. As its name suggests, the linear variable differential transformer works on the same principle as the AC transformer, but instead of supplying a load current or high voltage, it uses basic transformer principles of mutual inductance to measure linear movement. When two or more long solenoidal coils are wound together onto the same core, the magnetic flux produced by any one of the coils links to the other with the magnetic flux produced by driving coil, adding or opposing the flux produced by other coils. Thus, any AC current flowing through one coil will induce a voltage into the other magnetic coupled coils, and this is basic principle of the LVDT. The LVDT consists of three individual coils wound sequentially around a hollow, non-magnetic insulated tube. One coil of magnetic wire is classed as the primary coil, and the other coils form two identical secondaries. The two secondary coils are connected together in a series opposing configuration, that is, they are electrically 180 degree out of phase with each other. The LVDT's primary coil is energized by constant AC source with a frequency ranging between about 1 kHz to 10 kHz. The magnetic flux produced by primary winding is coupled through the core to one or both of the two secondary coils placed on either side of it. This arrangement produces a differential output voltage proportional to the core's displacement. A core is allowed to move freely in straight line inside a central hollow tube as a direct result of displacement of the connected object. This has the effect of increasing or decreasing the mutual inductance between the primary and the secondary coils. Due to magnetic linking of the coils, the movement of core in turn increases or decreases the voltage induced in each secondary coil, producing a very accurate device for measuring linear displacement whose output is proportional to the position of its movable core. Now this is the cross-sectional view of LVDT. These are two secondaries, and this is the primary coil energized by constant AC source, and this is the movable core. And this is basic construction of LVDT. Now we discussed about inductive transducer. So there are some advantages and there are some disadvantages of inductive transducer. So advantages of inductive transducer are the inductive transducers can work in any environmental conditions like humidity and high temperatures. This can give high performance in the industrial environment also. These have high frequency and stable operating range with a good lifespan. These can be operated at high switching rates in industrial applications. And the disadvantages of inductive transducer are the working and operating range of inductive transducer depends on construction and temperature conditions, and it also depends on magnetic field of the coil. Now some applications of inductive transducer. Inductive transducers are used as proximity sensors to measure position, dynamic motion, touchpads, etc., detection of metals and missing parts, counting the number of objects, linear and rotatory motion, galvanometers, LVDT and RVDT, pressure and airflow sensors, potential meters, sequential counters, PB monitor, heart monitors, and etc. Thank you. Have a nice day.